Now let's solve a slightly more difficult differential equation with the Laplace transform. Y double prime plus y equals t, and y at pi equals 0, at the same time as y prime at pi also equals 0. Now, the reason this is strange and will be a little bit more complicated is because of our Laplace transform for a derivative. Laplace transform of a derivative is s times the Laplace transform of the original function minus the function evaluated at 0. And if we took the second derivative, we would have a y prime at 0. This y of 0 is the reason why the Laplace transform is so well suited to solving initial value problems. But it is also unfortunate if we aren't given initial conditions at the point t equals 0. We're given at t equals pi, but there's a way that we can fix this. We can recover from this unfortunate event by defining a new function. Let's call this function z. Z of t, we will say colon equals means defined. We define z of t to be equal to y of t plus pi. Why would this work? No pun intended. Well, if we were able to somehow get this differential equation in terms of t, z of t, if it was in terms of z of t, then when we take all the Laplace transforms of derivatives, we're going to end up with a lot of z of zeros. And z of 0, by the definition of z, is equal to y of 0 plus pi, which is equal to y of pi. And we know y of pi. So in a way, in a sense, it's just like translating our function so that we get more useful take on the initial conditions. Alright, well, if we're going to be plugging this in, we need some expressions also for what z's derivatives are going to be. So z prime of t is just going to be y prime of t plus pi. No chain rule necessary. T plus pi. It's a weird plus. Z double prime of t is going to equal y double prime of t plus pi. And now we have to think how. How are we going to get our differential equation in terms of z? We can't exactly plug it in, because what we would need in order to plug something in is something like y of t plus pi. If we got y of t plus pi anywhere in our differential equation, we'd be able to say, great, we know y of t plus pi equals z of t, and we'll plug it in. We don't have any y of t plus pi's yet, but we could manufacture them, because in its full form, this differential equation actually says y double prime at t plus y at t equals t. And what we could say is, let's replace every t with t plus pi. And I'll tell you in a minute why this makes sense. Well, it makes sense, but why it works. Y double prime of t plus pi plus y of t plus pi equals t plus pi. And these are still separate things. Why can we just replace every t with t plus pi? In a way, it's because the differential equation is describing what's happening at any given time value, what this equation must look like. And we're actually not changing it. We're just saying, instead of the differential equation describing at any point t what happens at that same time t, the differential equation says, no, I'm going to tell you what happens at t plus pi. We still retain all the information, though. If we wanted to find what happens at y equals t, we just go to y equals t minus pi, and then we would be able to jump over to what happens at y at t. So we're not losing any information. We're just saying, let's jump ourselves forward. But this is great now, because now we have y double primes of t plus pi, y of t plus pi equals t plus pi, and what we can say is, yay, this is what our z's are. So now, if we plug in our z's, what we get is y double prime of t plus pi is z double prime of t. So we can even use red to celebrate. Z double prime of t plus, okay, no y prime, plus y of t plus pi. That's plus z of t equals, and then, okay, we have a t plus pi, but that's a good price to pay to actually be to solve this differential equation with Laplace transforms. Now, we can actually just apply the Laplace transform. So what we do is we take the Laplace transform of both sides. We're going to get, and I'm going to assume you kind of understand what's going on with the Laplace transform. So Laplace transform of z double prime of t, this is going to be s prime times big Z, the Laplace transform of t, minus s times z evaluated at 0, minus z prime evaluated at 0, plus big Z, and then this is all equal to t plus pi. And now it gets good, because now what we get is factor out the z. We get z times s squared plus 1, and then this z of 0, z prime of 0. Yes, this was the whole point of making z, is that z of 0, by definition, is y of 0 plus pi equals y of pi. And we know what y of pi is up there. So what we can do is say z of 0 equals y of pi. How convenient. Z of 0 equals y of pi equals 0. Z prime of 0 equals y prime at pi equals 0. What a nice differential equation. And now this all equals t plus pi. So, in conclusion, the Laplace transform of our function z of t equals t plus pi, all divided by s squared plus 1. And now, all that's left is, and wait a minute, what am I? Oh, yeah, of course. So, whenever you're taking the Laplace transform of both sides, it's usually helpful to actually take the Laplace transform of both of your sides. Probably all face-palming right now. Sorry. So, let's also take the Laplace transform of t plus pi. The Laplace transform of t plus pi is going to be, the Laplace transform of t is 1 over s squared, plus the Laplace transform of pi is pi over s. So, 1 over s squared plus pi over s. You know, we can simplify that a little bit if we multiply this one by s over s. And this is going to be 1 over s squared plus pi s over s squared, which can then merge the denominators to be 1 plus pi s over s squared. And now that we're also dividing by this, we can just take it down to the bottom, and we get pi s plus 1 over s squared times s squared plus 1. This is what the Laplace transform of z is. Now, if we could just find what the inverse Laplace transform of this right-hand side is, we will be golden. And I want to show you a little trick. By no means do you have to remember this trick, but if you would like to remember it, then it is a much easier way for solving partial fraction decompositions if a specific case is true. If it so happens that you have this and this, both of your multipliers in the denominator, if we call this big X and we call this big Y, if it so happens that Y minus X has no S's, I can just prove this to you quickly as a little trick, is that 1 over X, Y equals 1 over Y minus X times 1 over Y minus, let's not confuse this, 1 over Y minus 1 over X. It's possible that I messed up some kind of a sign here, but this is what it is. The reason is because if we take this right-hand side and we just multiply everything through, or sorry, if we multiply this by x over x and this by y over y, we get that 1 over xy equals 1 over y minus x times, and then yy, so y minus x over xy, common denominators. These go away, and we're left with 1 over xy is indeed 1 over xy. So, in short, if we have it so that x minus y has no s's, which, I mean, it makes sense. If x minus y has s's, then what you're going to be left with is something here that actually contains s's, which will then make it another partial fraction decomposition, which is even worse. But in our case, the reason I even brought this up is s squared plus 1 minus s squared would have no s's. It would equal 1, and we'd be to use this special case of partial fraction decomposition. So, what we can say is that this then equals pi s, I'll write it like this, pi s times this special case for partial fraction decomposition, where you have 1 over y minus x. Y minus x is s squared plus 1 minus s squared. That's just 1. Times, and then the inside here is 1 over y, so 1 over s squared plus 1, minus 1 over x, 1 over s squared. So now we get is that the Laplace transform of z of t. And by the way, this was just a side note. It's an easier way to solve partial fraction decompositions if this special case occurs. By no means do you have to remember it. If you did partial fraction decomposition, you get your answer just fine. It would take a bit more work, though. The Laplace transform of z of t equals pi times s times 1 over s squared plus 1 minus 1 over s squared. Now, if we distribute things, we get this is going to equal pi s over s squared plus 1 minus pi s over s squared, which is just pi over s. Fantastic! Now, we really actually shouldn't have distributed the pi, so I'm going to refactor it. It's just the s that we wanted to distribute. So, if we say pi times all of this, now we're left with two things that we know how to take the Laplace transform of. Because if this is what the Laplace transform of z of t looks like, then z of t must equal the inverse Laplace transform. And I'm going to pull out the pi, because again, inverse Laplace transform is linear. The inverse Laplace transform of, let's get a nicer curly brace, of s over s squared plus 1 minus 1 over s. So what we get is z of t equals, let's do it in green because we're nearing the conclusion, equals pi, although a green pi doesn't look too tasty, times the inverse Laplace transform of s over s squared plus 1. That looks a lot like the cosine of 1t. So this is indeed the cosine of 1t, it's just t, minus inverse Laplace transform of 1 over s. That's just 1. So what we're left with is that this equals pi times the cosine of t minus 1. Don't box this answer, though, because this is not the final answer. If we remember, we specifically designed z as a translation. This is the definition of z, with that colon equals meaning definition. This is the definition of z as a translation of y, so that y's initial values later wouldn't hurt us when we're trying to do the Laplace transform of it. So, if z of t is y of t plus pi, we can just write that down here again. So, z of t equals y of t plus pi. Because of this, we know that z of t is this. That's not actually y of t. If we say, though, that, so z of t equals y of t plus pi, if we said that, say, v equals, that's not the color I was looking for, v equals t plus pi, then y of v would equal z of, well, based on v's definition, t equals v minus pi. V minus pi. And then we could again just say, okay, v, t, all the same thing. So we get that our solution, y of t, any variable, just whatever you plug in, is z of that variable minus pi. So really, we had 3 steps. We had step 1 was translate so that the initial values made sense. Step 2 was solve, and that in of itself it had the 3 steps that we talked about. And then step 3 was untranslate. Just go back to where you were before, because we do need to have an untranslated solution. So, get ready for the epic conclusion. What we have now is that y of t equals z of t minus pi. Z of t minus pi is pi times the cosine of t minus pi, and the cosine of t minus pi is just negative cosine of t, so we can do that this is all just negative pi times the cosine of t minus 1. That is our final solution, so enjoy it. Alright, I'll see you in the next video.